This is a Physics 2212 Measuring Excess Electrostatic Charge on Ordinary Objects lab report. The introduction of this lab is to utilize ordinary objects, in this case a piece of clear tape, to determine the excess electric charge that remains on it, utilizing computational modeling, computer programming, physical experimentation, and observations. The objective is to determine how force is affected by distribution of electric charge and determine the electrostatic charge acquired by clear tape. The models and fundamental physical principles utilized in this lab are those of Coulomb's law, interactions between force and electric fields, and Newton's second law, as a floating tape piece is in static equilibrium. A brief preview of the main result of the lab is that the charge on a piece of clear tape came out to be approximately 2.0 times 10 to the negative 8 when utilizing a point charge type model, and 2.6 times 10 to the negative 8 when utilizing a line charge model. The experimental procedures and observations are that the setup included making 2 U-tapes from clear tape. Each tape had a length of 0.2 meters with a mass of 1 gram per meter and tape mass of 2 times 0 times 10 to the negative 4 kg. A strip of clear tape was pulled off the base tape layer. Due to forces of repulsion, one tape floated above the other piece of tape, meaning they both carry like signs. The floating distance was calculated to be approximately 0.043 meters. An observation was made that the U-tape was attracted to the hand, which had a neutral charge. This supports that induced polarization creates a net overall attractive force. The main physics ideas are Coulomb's law, gravitational force, electric field, electric charge, gravity, and Newton's second law. Gravitational force is modeled as Fg equals mg. In this case, both are equal to 1.96 times 10 to the negative 3 newtons. At equilibrium, the force of gravity is equal to electric force, so Fe equals Fg. With a system of upper tape and the surroundings of the lower tape and the Earth, because the upper tape is stationary in nature, acceleration is equal to 0, which means F net equals 0. Looking at the free body diagram, there are 2 vertical forces acting on the tape when it is not in motion. The force is gravity, which acts downwards, and electrostatic repulsion, which acts upwards. Due to the tape being in static equilibrium, the forces must be equal to each other. For computational model 1, in the case of determining the charge for point charge approximation, Fe is equal to 1 divided by 4 times pi times e naught times q squared divided by d raised to the power 2, and turns out to be 2 times 10 to the negative 8 c. For the calculations of excess electrons, n turns out to be 1.25 times 10 to the negative 11, 10 to the positive 11 electrons. Rearranging Coulomb's law to solve for Q, we get a net charge of 2 times 10 to the negative 8 coulombs, which is about 125 billion excess in coulombs. The point charge approximation treats this tape as one point charge, with the charge located at the center of the geometric center of the tape. The comparison for the point charge code is that the models of both tapes are shown as single 3D spheres with an upwards arrow located on the top sphere and downwards arrow on the bottom one. The force and electric field of the single point is then calculated, with Q point equals 2.0 times 10 to the negative 8c. The assumption in this case is made that the tapes have uniformly distributed net charge, and the charge is concentrated at a single point at the center of the tape. The model also makes the assumption that the charge is present at the minimum possible distance, d equals 4.3. For the line charge code, however, the V pipeline demonstrates how there are many spheres that form 2 lines parallel to each other. The discussion is that if the electrons were positive and protons negative, then there would be no change in the observed experiment. This is due to the fact that like charges would still repel. It is critical to handle the tapes carefully because allowing the tape to come into contact with skin allows electrons to escape both ways, which leads to a minimization of the net charge of the tape. This leads to a reduction of the net electrostatic force, causing it to fail to float. In conclusion, this experiment demonstrates the way in which electrostatic forces are able to balance gravitational ones in everyday objects. The net charge was determined on a piece of clear tape using principles of physics and different computational models.